in the recent class that I gave you some subtopic on heat conduction equation. Okay, the general heat conduction equation, and then from there we need to identify how to use that equation as well as identify the boundary condition. I'm not sure whether you have finished. I assume that you already watched the video, okay, and then try to understand the video as well as compare with my lecture note, lecture slide, and do some understanding or try to understand the exercise that written in your textbook. Okay, whether you want whether you already try or you just read it, I'm not sure, but I hope you can understand that. Okay, because I will repeat again the process here, but in the much more brief. Okay. So previously we learned about the general heat conduction equation. I think this one. Okay, this is general heat conduction equation that you may use for any kind of problems related to the three-dimensional case, okay, of Cartesian coordinate. Okay, so from this equation we need to identify what is the boundary condition. Okay, so from here there is some simplification. I think I'm not going to explain this because I believe we just concentrate on the general heat conduction equation, this one. Okay, so this is the general heat conduction equation. Okay, that is my pen. General heat conduction that you need to use in most of the case of three-dimensional Cartesian coordinate, and then apart from that you need. So if you look to the boundary condition, boundary and initial conditions, okay, there is about, I think, 6. Okay, here in the slide there is a 6 type of boundary condition. Okay, constant temperature, constant heat flux, okay, convective condition, radiation, interface, okay, and generalized condition. Okay, what I can say, the most typical or the most common condition that may use in the heat transfer problem is the first 3, this one. Okay, this is what explained in the video that I okay, so these 3 common boundary condition will be applied. Okay, apply plus the general heat conduction equation, okay, in order to use to solve the problem of heat transfer conduction. Okay, I'm not go detail in the boundary condition. I'm assuming that you have read this. Okay, we will try to understand more in the example. Okay, so this is the example that I ask you to understand. Okay, okay, let me find the example in the textbook section. Example 210. Okay, this one. Okay, example 210. I believe all of you already download the textbook that shared by your friends in the WhatsApp group. So try use these ebooks. I mean, if you have a hard copy, it is much better. But if you don't plan to have a hard copy, then please have the soft copy and read it truly, so that you can understand the example, because most of the example is taking from this textbook. Okay, this is the example. Okay, so from the example we try to understand the problems, okay, by drawing the schematic. Okay, so this is the schematic of the problems. Okay, so this is the schematic of the problems, this one. Okay, so you have a system which is in this case is a plain wall. The condition, okay, where the temperature on one side is a T1 and you have another temperature condition in the other side with T2, okay, and you have the thickness, okay, of the wall with L equals to 0.2 meter, okay, here L, which is L here is 0.2 meter, okay. Is given here T1 120, T2 50, okay. And then the question asks you to find the variation temperature within the wall, okay, and the value of the temperature at x 0.1, that is for the question A, and for the question B is the rate of heat conduction. Okay, I will not go through to the problem yet, okay, but I want to show you how this general heat conduction equation utilize as well as the boundary condition. Okay, so in this example they just giving you this equation. Okay, so it's quite simple, but you might asking how this equation come from. Okay, so originally the equation should be using this general heat conduction equation. So where is our general heat conduction equation? So this is the long one, this one. Okay, so this should be your general heat conduction equation. So this means, so in order for you to solve this problem, okay, supposed to be you need to write, I mean before you reach this step, you need to state the general heat conduction equation is that long. Okay, so let's say I give, let's say we try to do this in the plain A4 by doing originally from scratch. Okay, so first, like I say, you need to draw the schematic of the problem. Okay, so this is what given in the example here, the schematic. So this is the first one. Okay, and then second, you need to find the second you need to identify or state the assumption, okay, of the problems. So that's why by stating the assumption, okay, by stating the assumption, you know that there is limitation of this problem, okay, and this limitation can be used to simplifying the equation to the more suitable equation that you can solve for this particular problem. Okay, so if you look to this textbook, okay, the common assumption or the suitable assumption for this problem is, first, heat conduction is steady. Okay, that particular assumption is very useful in order to simplify the equation. Okay, So first is a steady state condition. Okay, steady state condition. Second, heat conduction under one dimensional analysis, one dimensional heat conduction analysis. Okay, and then the third one, you have the thermal conductivity. Okay, in fact, in the second one, the example in textbook give you some quite long assumption. Heat conduction is one dimensional since the wall is large relative to its thickness and the thermal condition on both sides are uniform. Okay, because this is to support why you need to say it is one dimensional analysis. Okay, because someone will argue why this is one dimensional, why not two dimensional. Okay, so since the argument is say that the wall is large compared to the thickness, so that means the heat transfer on the y direction probably can be negligible. Okay, so for example, if I can draw, I can draw the, it's a bit difficult to draw a straight line here. Yeah, I go to the image. Okay, so we assume only one dimensional because we say that the wall size, okay, so this means this size, okay, this let's say this is A and this is the B. Okay, so the A dimension is large enough compared to B. I can put 3, large enough. So that's mean heat transfer through the y direction Q is, we can say, is a 0. We only consider heat transfer through the x direction. Okay, so if you say that there is some heat transfer through y direction, heat transfer to x direction, that means it is not one dimensional, it is two dimensional heat transfer analysis. Then you have to consider the y as well. Okay, so because of this, the wall is large relative to its thickness, so we can say that the y direction can be negligible because the thickness is so small compared to the size of the wall. Okay, so that is the second assumption. Okay, the third assumption is a thermal conductivity constant. Okay, the K value is constant. Okay, K value is a constant. K constant. K value constant. Okay, and number 4, K value constant, I think it is supporting the isotropic condition because we assume that the layer have homogeneous material where the thermal conductivity is same value regardless of any direction x, y, and z. Okay, and the last one, there is no heat generation. Okay, so no heat generation because there is no information given about the heat generation. Okay, so no heat generation here. No heat generation. Okay, so if you look back to the equation, okay, if I can so okay, suppose after assumption you need to find the properties, okay, but since the problem is give you the properties, okay, so you just restate the properties value of the wall. So the properties of K for the wall, okay, is a how much? 1.2, is it 1.2? Yeah, 1.2 watt per meter Kelvin. Okay, so then the next one you need to do the analysis. Okay, so the analysis. Okay, so suppose in order to start the analysis, you should start with the general heat conduction equation. So using general heat conduction equation, okay, so you have okay, I need to rewrite again the equation. Okay, probably you don't need to remember this because normally this sometimes given or sometimes you can taking direct from the textbook. Okay, plus E dot generation equals to rho C dt over D time. Okay, so this is the general heat conduction equation that you should use this. Okay, so based on the assumption, okay, so because of the assumption, the first assumption says steady state condition, so this means all the properties will be constant regardless of time difference. Okay, so because of the assumption, first this one will become 0, or you will not consider these terms. Okay, because this is steady state. Okay, 0 because of steady state. Okay, and then the second, because of one dimensional heat conduction analysis, so you will not consider the y and the z. Okay, so this is a 1D, so this is a 1D, so you only consider x. Okay, because of the x is your interest. It might be y, the x is also 0. Okay, depending on your schematic or your how you sketch the system. Okay, the third one, k constant. Okay, so the k constant is basically just to show that isotropic value. Okay, because of you only consider now only one dimensional, so the effect of k constant not really significant. Okay, because you might put it the k in term of e generation k. I mean, you can throw it the k to the right side, the right term, and you can remove the k term. Okay, and the fourth one is a no heat generation. That means there is no term of heat generation here. So this is for the no heat generation. Okay, so the remaining term is only this term. Okay, and if you rearrange this equation, okay, so if you rearrange this equation or you write back the equations, okay, k delta t over delta x equals to 0. but because of this is only the only this is the only parameter that available in the equation. Okay, so you change this to the normal derivative, normal differentiations. Okay, and this will become over dx equals to 0. Okay, because the k term is a constant, it is so you can remove the k terms, and this is the final general heat conduction equation for this problem. Okay, so from here to here is basically depending on your assumption, and where you got this assumption is from the problem's explanation, or from the problem description. So you need to know whether it is really useful to define one-dimensional or two-dimensional, or you need to consider all three-dimensional axes or three axes, as well as other information. Okay, generation. Okay, so this is the first one. So this is your mathematical expression for this problem. Okay, so mathematical expression for the current problem. Okay, with boundary condition. Okay, so the bond is given in the so if you look back to the problems, okay, this one. So they give you the condition of constant temperature. Okay, constant temperature of T1 and T2. So basically this is your boundary condition. Okay, originally it should be Tx equals to T x Tx. Okay, so at T0, okay, the Tx equals to T1, which is 120 degrees Celsius. Okay, and at TL equals to TL, which is equals to T2 equals to 50 degrees Celsius. Okay, so if you do the step, okay, so this is the first one. So the second, you need to draw the you need to state the with a boundary condition T 0 equals to T1 equals to 120 degrees Celsius, and T L equals to T2 equals to 50 degree Celsius. So this is your boundary condition. At least you should have a two boundary condition in order to solve the problem. Okay, so you need to have this and you need to have this, then you can solve this problem by doing some differentiation of the equation with the boundary condition. In fact, you need to do some integration. Okay, so if you look to the problem here, okay, so by having this boundary condition and the general heat conduction equation, the simplified equation, then you need to do some integration step. Okay, so from here you need to integrate in order to get the terms. Okay, so this is where you apply back your knowledge in the engineering mathematics. Okay, I believe all of you already took this course. okay, and then second integration, okay, second order integration in order to get another terms of C1 and C2. Okay, this is the first term, or this is the first level of integration, and then this is the second level of integration, and using some by combining the equation with the boundary condition. Okay, so you need to solve the expression of the temperature, okay, inside the wall. So this is, so they say that this is a so-called the general solution. Okay, I sometimes I'm called this as a temperature variation, okay, as a function of thickness x, okay, of the wall thickness, if you want to put more details statement. The temperature variation s, okay, as a function of the wall thickness x, okay. So from the boundary conditions, so you can find what is the L value, sorry, what is the yeah, L value, and you can solve this in the next step. Okay, so normally from these equations, okay, this is the mathematical expression, okay, and then from the mathematical expression you find the temperature variations, okay, and finally you use the temperature variation, the equation, to find with the what temperature you want to find at along the wall thickness. Okay, for example, here you want to find the temperature at 0.1 meter, because it is already stated in the problem. Here, where is the problem? Yeah, this one. Okay, you need to find first the variation of temperature within the wall, which is Tx, and the value of temperature at x 0.1 meter. So you need to find the temperature at 0.1 meter and the rate of heat conduction. The rate of heat conduction, basically you differentiate back the equation, okay, based on the thickness, dt dx. You know the k value, you know the area, you do the differentiation for this particular equation, temperature, and you can get the heat transfer calculation based on this equation. So basically this is the general heat conduction equation. Where is that? Yeah, this one. Okay, so from here you can find the value of the parameter, and you can get the 6300 watt. Okay, so that is the first example. Okay, so if you look to the next example, any question before that? Okay, so it's quite straightforward because this is the simplest boundary condition. Okay, so this is the boundary condition which this is a temperature constant. Okay, so if you look the second example, it is example where the boundary condition have the different condition, like the heat flux. This is a heat flux boundary condition. Okay, so this is the heat flux boundary condition. Heat flux BC. I put a BC as a boundary condition. This is a T constant boundary condition. Okay. How about this? This is another heat flux. So this is a heat flux as well. This is also another heat flux, but this is heat flux with a negative value. This is a heat flux with a positive value. Okay. So basically, this example just varying the boundary condition. So what happened to the boundary condition? What happened to the equation when you vary the boundary condition? Okay. In fact, yeah, this is how they solve this. I think you can. This is only for the. I think this is A. Okay. This is a temperature variation for the first boundary condition. Okay. And then for the B. Okay. So for the B, in this case, the different heat flux are specified at two boundary, so there is no solution. So this means the second condition cannot be solved. Okay. While for the C, so this is the temperature distribution for the boundary condition. So even though your general heat conduction equation is the same, but if your boundary condition is different, so you might get the different temperature variation across the wall thickness. Okay, so you need to identify, or you need to find the right boundary condition for a particular problem of heat transfer. Okay, this is another example that I ask you to read through, or to try, or to understand. Okay, so this the example 212 is a heat conduction based on the ion system, or the electric ion system in the base plate. So this is the example. In fact, you don't need to draw the ion, but you can simplify into the wall, and with the some resistant heater in the left side, and constant, or not say constant, is a condition of the open environment in the right side. Okay, so if you look, so this is the condition, this is the all the parameter given. Okay, so first you need to state the assumption. Okay, heat transfer is still steady, heat transfer is one dimensional. Okay, thermal conductivity is a constant, there is no heat generation in the medium. So in this case, the medium is your base plate. Okay, so your base plate is your medium. Okay, so your system is this. I'm not really good to draw in the. Okay, so if I can draw, this is the plate that you are interested. Okay, not the iron, not the resistant heater. So this is the only plate that you want to analyze. Okay, because if you look here, if I can draw back the plate. Okay, so this is the plate that you want to consider. On this side, you have the heat flux, or you have this so-called resistant heater. How can I draw the heat flux? Okay, if I use the. So here, so this is the heat flux. Okay, since this, let's say you are considering this is the xy, so heat flux S here is a Q0. So Q0, what is the Q0? So Q0 is this one. So how you get this value is basically the heat produced by the iron, 1200, divided by the area of that particular base plate. which is here 300. So 1200 divided by not say 300 because it is in centimeter cube, centimeter squared. So you need to change into meter squared. So it's basically 4000 watt per meter squared because this is the heat flux. Okay, heat flux from the heater element of iron. Okay, so this is a 4000 watt per meter squared. So if you look back the heat conduction equations, so with the assumption here, it will fall back to the same heat conduction equation. So this is your the simplified heat general heat conduction equation. Simplify heat conduction equation. Okay, so no yz, k is constant, no heat generation at for the base plate. Okay, we consider base plate. You might say that there is heat generation in the resistor heater, but we don't study resistor heater, we study the base plate because the base plate is of an iron that you want to consider. Okay, you want to study the base plate, you don't want to study the resistor heater. Okay, that is the heat conduction equation. And again, the next one, you need the boundary condition. Normally you still need to have a two boundary condition. The first one is on um, the left side, or the left side of the wall, because this is considered wall. So in the wall, the first one is basically is the wall exposed to the heat flux. Okay, so at this, okay, at this condition, so at t equals to 0, the value of the heat flux equals to 4000 watt per meter squared. Okay, so because 0 is from here, this is a 0, this is x equals to L. Okay, so this is where the so I can say this is when x equals to 0, and this is x equals to L. Okay, so because in the left side it is exposed to the heat flux, this is your boundary condition. And in the right side, because of it is exposed to the convection, so this is convective boundary condition. This is a heat flux boundary condition. This is convective boundary condition. Why? Because at x equal to L, the wall is exposing the system to the heat transfer by convection. Okay, so using this, okay, so this is the mathematical expression. So the mathematical expression for this problem, the mathematical expression of this problem is this one, and with this boundary condition 1 and 2. Okay, so once you have a mathematical expression, so you need to solve this using integration. Okay, so you look here, from here they integrate, okay, to find the value, and finally you got this term of temperature variation as a function of wall thickness. Okay, with regard the boundary condition exposed to the heat flux and heat transfer by convection. Okay, so you can see it's totally different when it is boundary condition using the temperature constant. Okay, any question? So with this one you can solve this equation if you want to find T at zero value. So this is temperature at X equals to 0. So if you want to find X equals to half of the thickness, then you can find the value. Okay, so the Tx equals to half L will be what? It's depending on the equation. You just apply back the equation. Okay. Any question? Actually, there is several example in the textbook. Okay, I think in fact in the textbook also show you how to solve the problem of cylindrical coordinate. Okay, I not go through because we don't have sufficient time to discuss in detail, but actually if you look to the example that discussing the cylindrical case, so it's like a similar step, okay, as you are in the Cartesian coordinate or xyz coordinate. Okay, same goes for the spherical. Okay, if you go to the cylindrical, there is example at 215, and for the spherical for 216. Okay, I want to give some example that probably related to the some exercise in the textbook. Okay, in fact I put it as a assignment, but don't take as assignment first because I'm not decided yet your assignment. Okay, this one. Yeah, example. This one. Okay. So this example is actually in the textbook exercise in the textbook. Okay. So this example is basically exercise in 240 or N41 problems in your textbook. Okay. So this example is about a steel pan used to boil off water on top of an electric range. Electric range ni is actually is a electric cooker, electric stove. Okay. So the bottom section of the pan is 0.3 centimeter thickness and diameter of 20. Seems like you need to solve using a cylindrical coordinate, but you need to identify whether you need to solve using cylindrical coordinate because of the pan is like a cylinder, or you want to solve using a plain wall, a simple plain wall problem or analysis. Okay, so if you look to the explanation, the electric heating unit of the range top consume 1250 watt. Okay, so this means the heat produced by the cooker, okay, is 1250 watt, and only 85% of the heat is generated. Okay, so 1250 watt will be used to heat up the pan because of probably there is some heat losses to the cooker itself. Okay, and heat transfer from the top of the surface of the bottom section to the water is by convection. Okay, So basically you want to consider the bottom section. Okay, so your interested section is the bottom section. So if I can draw this, so this is your bottom section of the pressure steel pan. Okay, bottom section. Okay, so the L is the thickness. So basically this is the thickness, 0.8. And then the diameter of the section is a 20 centimeter. Okay, and there is a heat flux here. And here it is exposed to the water. Because of it is heat produced to the water, to the liquid. So basically this is the convective boundary conditions. Okay, so the problem say heat transfer from the top surface of the bottom section to the water is by convection. Okay, they give you a H value. Assuming constant thermal conductivity, one-dimensional heat transfer. See, this is the assumption. Thermal conductivity is a constant. Okay, and then one-dimensional heat transfer, so that you don't really apply the y and z's. Okay, express the mathematical formulation. See, express the mathematical formulation, meaning what you need to include in the mathematical formulation: the general heat conduction equation and the boundary condition. Okay, so is highlight here, do not solve the problem, meaning you don't need to do the integration. When it is mentioned do not solve, in fact, if you go to the textbook, do not solve mean you don't need to do integration. You just state the heat conduction equation and the boundary condition. Okay, I think so if you want to answer this so let's say you want to solve this problem. Okay, so first you need to have, okay, assuming that you know to do this, first you need to draw the schematic. You need to state your assumption. Okay, then you need to define the properties that probably required for your analysis. Properties why the can you see clearly my slide?
Yes, doctor.
Okay, because I saw from my phone it's not really clear. Okay, thanks guy. Okay, properties, and the second, the analysis. Okay, so draw the schematic. Okay, whether you want to draw as in the vertical shape, or you want to draw in the sorry, horizontal or vertical, is up to you. But make sure when you want to change the orientation, you are still using the same dimension. Okay, you also can use this, or you can put it like this as well. Okay, and then state the assumption. Okay, the properties probably in here is the k value. The k value, in fact, H value for the fluid. Okay, if it is given, otherwise it is just leave as it is, and the analysis. Okay, so from the general heat conduction equation, so the final mathematical expression or mathematical formulation for this particular problem is basically delta squared t divided by dx squared, okay, equals to 0. Okay, so this is a common for one dimensional case. Okay, in fact, for your level, normally we only simplify from this long equation. Okay, from this long equation, where is it? This one? Yeah, this one, from the long equation into the very simple expression. Okay, this one. Okay, and then the boundary condition with boundary condition. So what is the boundary condition? So if you look to the problem, the boundary condition, okay, at x equals to 0, okay, at x equals to 0, the heat flux, okay, equals to, so you need to find the heat flux, q dot s divided by heat by the electrics, not s, e, I think, area. Okay, okay, so this one equals to 1250 watt, okay, divided by pi d squared. What is the diameter? So the diameter here is 20 centimeter. So basically 0.2 to the power of 4 divided by d. Sorry, divided by 4. 0.2 to the power of 2, not 4, to the power of 2 divided by 4. Okay, and this you will get some value of the heat flux. Okay, how much this one? 1000 39,788 watt. Okay, so due to heat losses, only 85% it reach the base plate. Okay, so Q dot 0 actual equals to 0.85 times 39788. Okay, so probably you got a value of 33,280 watt per meter square. Okay, sorry, this is per meter square. Okay, watt per meter square. So the boundary condition at first is equals to, so first boundary condition, okay, is basically negative K dt at x equals to 0 divided by dx equals to 33280 watt per meter square. So this is the first one. Okay, and the second condition of the boundary condition, okay, is due to convection. Okay, so negative K dt at L divided by dx equals to H TL minus T surrounding. Okay, so this is the second condition. So basically you have three mathematical formulation for this problem. Okay, which is, this is the first one, this is the second one, and this is the third one. Okay, so using all three equations of I think this is the final. I mean you just need to state, you don't need to solve. Okay, so once you want to solve, okay, so you need to use all this equation, using all three equation, do some integration and find the temperature variation. Okay, so in the problem we say that you cannot, you don't need to solve because you just need to reach until this point. So once you want to solve it, then you can apply the knowledge of your mathematical understanding in terms of integration, okay, and some equation, one or two more equation to solve the problem, to find the unknown value of C1, C2 for this particular integration. Okay, okay, that is for the first example given in the textbook or given in the slide as well. Okay, So you look here, this is the problem. So I show you the parameter that might important for your problems, and then what you need to highlight the requirement of the problems, okay, and you can solve by expressing, only expressing, you don't need to solve, okay. So here you need to express, you don't need to solve, do not solve the problem, okay. There is another example, okay, I think, sorry, yeah, this one. Here, this one is exercise of the spherical concept, spherical coordinate, okay. This is spherical related to the heat transfer convection condition, boundary condition. Okay, I will not go through this. Okay, I want to discuss about this example. Okay, it's not really assignment yet because I will give you the assignment in the e-learning, but probably we want to discuss the next example of this plane wall, okay, where the thickness is given and the boundary condition is slightly differ from your problems given in the previous slide. Any question so far? Any? Everyone is okay?
Okay, doctor.
Okay, thank you. How many of you still attend today? Participant, where is my participant? Okay, all is come. I think there is 5 or 6 of you is not come to my class today. Okay, because it's supposed to be 67 or 68. Okay, never mind. I just need to note who those who not coming. Okay, so this is another exercise that you can obtain from the textbook. Okay, so if you look to this assignment, not say assignment, I mean the exercise, I will give you the exercise later in the e-learnings. So this is related to the example in 258. Okay, so in this example you need to solve. Okay, so you need to solve this problem. How can I copy this so that I can draw some sketch behind the problem? Can I? No. 257 is it? Or sorry, 258. Okay. This is a large plane wall thickness. Okay. I think we just draw from the. Probably I can put side by side. Can you see now? Is this in side by side?
Yes, doctor.
Okay. Okay. Okay, this is the problem of 258. if you have a textbook, you can go to the problem 258. Okay. Okay. So first you need to draw the schematic. So it's basically a large plain wall. Okay, so you have, it should be straight line. Okay, my sketching is not good enough. So this is your L. Okay, and this wall have a K value. We'll define later. The surface area of 30 meters squared. Okay, the left side of the wall is maintained at a constant temperature T1. Okay, so if this is your Y, X, okay, the left side, so this means here is your T1. Okay, so T1 equals to 90 degrees Celsius. Okay, while the right side loses heat by convection to surrounding air at 25 degrees Celsius. So here there is a convective environment. Okay, where the temperature of surrounding equals to 25 degrees Celsius and the H value equals to 24 watt per meter squared Kelvin. Okay, so that is your schematics. Okay, so next one you should put your assumption. Okay, so you need to put assumption for this problem. So what is the assumption? Okay, first, I think it's quite similar with the previous example. Okay, it's a plain wall with a steady heat conduction. Okay, plain wall with steady state condition. Okay, and then heat conduction, because it is only give you some one dimensional, so you can say that it is a one dimensional heat conduction equation. In fact, it's give you here, I mean, assuming constant thermal conductivity and no heat generation in the wall. Okay, you can by reading back the problem, you can put some of the assumption is already given in the problem. Okay, constant thermal conductivity, no heat generation, steady, one dimensional. So this is the assumption that can apply, can you use and simplify the equation. Okay, so a plain wall, if I write back steady state and then constant thermal conductivity, and then no heat generation. Okay, and then what else? Constant thermal conductivity. no heat generation, steady one-dimensional analysis, one-dimensional 1D analysis. Okay. Okay, next one, the properties. So what is the properties given? Okay, K of wall of plane wall equals to 1.8 watt per meter Kelvin. Okay, I think there is another value H of convective environment. Is a 24 watt per meter squared Kelvin. In fact, some of the textbook did not mention about this H value because it is represent the value of convective coefficient of the fluid. But because I think that this is a part of the thermal properties that you need to know in the problem, then you can write in the properties section. Okay. Next one is the analysis. Okay. So the analysis, I think based on the assumption. Okay. First, we simplify the general heat conduction using general heat conduction equation with simplification based on assumption. So your final mathematical expression for this problem equals to, again, same, this one. Okay, with boundary condition 1 at t x equals to 0, t equals to T1, which is 90 degrees Celsius. Okay, this one. Okay, the second condition. Okay, so due to convective environment, okay, so the boundary condition negative K dt for that particular temperature L divided by dx equals to H T L minus T at the surrounding. Okay, so this is your, oh, I don't have any more A4 for space to write this one. So if I can see, if I can label this into the what is the pen? If I can, so you have a 1, you have a 2, and you have a 3. So using these three expression of problems, three mathematical expression for this problem. So do some integration. Okay. Let's say we try do this. How to draw? How to erase as? You know, cannot choose. Okay, never mind. I try to utilize the space is given here. Okay. So dt dx equals to c1. So you integrate more tx equals to c1x plus c2. Okay. So using boundary condition, x equals to 0. So the T0 equals to 90 degrees Celsius and x equals to L. Then this is a bit, I think you don't need to use this for the time being. You just use the first terms of temperature at x0. Okay. So you know that at t equals to 0, C1 times 0 plus C2 equals to 90 degrees Celsius. Okay, so basically C2 equals to 90 degrees Celsius or equals to T1 because 90 degrees Celsius is a T1 here. Okay, so you can, okay, first you can find C2 and then again you use another equation at T equals to L to find the C1. Okay, and finally you can, once you can know the C1 and C2, you can find the expression of the temperature as a function of x. Okay, so that is your aim. So I hope you can try this. Okay, and then from that particular equation you can, okay, so what is the question actually? First, express the differential equation and the boundary condition for this case. So basically, this is the first answer. Okay, so this is the A. Okay, so this one, and this one. Okay, that is the part A. Express the differential equation and the boundary condition for one-dimensional heat conduction through the wall. Obtain relation for the variation temperature in the wall. So this is the B. Okay, so this is the B. This is the B answer. So the B answer should be Tx is a function of what? Okay, Tx as a function of what equation? Okay, and C, evaluate heat transfer. So how you want to evaluate heat transfer? Okay, wait, find some space here. Let's say I do it here. Okay, so C, evaluate the rate of heat transfer through the wall. So the rate of heat transfer to the wall is basically the rate of heat by conduction. Sorry for my nice handwriting skill. So I hope you can understand this. Rate of heat by conduction, because heat transfer to the wall is only by conduction. Again, there is no convection, there is no radiation for inside the wall. Okay, so rate of heat by conduction you can get by negative KE dt dx. Okay, so by calculating dt dx, what is a dt dx? If you look here, dt dx, where is the equation just now? Yeah, dt dx is a C1 here. Okay, so basically this one equals to negative KE C1. So so still you need to find C1 because I don't find C1 here, because normally when you find C2, the next one you can find the C1. Once you find the C2, then you can find the C1, this one. Okay, before you want to find the final temperature variation of X, okay, of Tx. So first you need to find the C2, C1 and Tx. Okay, so once you find the Tx, then you can get of heat transfer through the wall, this one. Okay, well, you still need to solve this, okay, because there is some relation related to the H value as well as the K value. Okay, so once you get the terms, okay, you find the value and you should get the rate heat transfer in the watt, in what will in joule per second or watt terms. Okay, okay, any question? I hope you can follow, because I'm writing quite I'm writing the step is not in the right sequence. Okay, I just find wherever I got a space, okay, then I write it. So if you not really understand, please inform me so that I can repeat that. Okay, so that is for this example. Okay, example of plane wall. Quite I can say it's quite straightforward. Okay, the only thing that you just need to understand how to solve the problem by having the mathematical formulation. Some of you might thinking that what happened if we need to consider two-dimensional or three-dimensional, or probably you have more weird boundary condition. Okay, so if you look to this textbook, okay, in this early part solution, okay, this one, okay, look here or read here. In this section we will solve a wide range heat conduction problem of rectangular, cylindrical and spherical. Okay, however, we limit our attention to the problem that result in ordinary or normal differential equation, such as steady, one-dimensional heat conduction problem. So this means you will not get a problem. You might get to express, but you don't need to solve. Okay, so don't worry that you say that, oh, if there is two-dimensional, we don't have a time to solve this problem. No worries, as long as you know how to express, that's all. Okay, you don't need to solve a problem that probably related to the two-dimensional analysis. Okay, you just need to express, but you don't need to solve. Okay, even here you say we will also assume constant thermal conductivity. Okay, so that's why in this textbook it is already simplify the problem that you may use to do the analysis of heat transfer. Okay, I don't show any example of cylindrical and spherical, but if you want to look, if you want to see the example of the cylinder, I think the example of 215, yeah, this one 215 is about the cylindrical shape or cylindrical coordinate. Okay, see here how they express the mathematical formulation, okay, and the two boundary condition. Okay, so this is just state or express. You don't need to solve. Okay, once the problem asks you to solve, so this is how you need to solve the problem. Okay, so by solving, then you need to do some differential equation, first differential equation for the first part, and second first integration and the second integration. Okay, and then you need to find the temperature variation as a function of normal x in this cylinder as a function of radius. Okay, so once you find the temperature variation as a function of radius, you can calculate the heat transfer by conduction, okay, by calculating negative Ka dt dr, not dt dx. Dx is only for the Cartesian coordinate. Okay, Q conduction equals to negative Ka dt dx for the Cartesian. For the conduction cylindrical, so negative Ka dt over dr. Okay, because it's a function of radius. Same goes to the spherical. Okay, so the spherical, this is your mathematical formulation. This is your mathematical formulation. This is your boundary condition. Okay, so these two is you just need to state. Okay, one you need to solve, then you have to do some integration. Okay, integration until finally you got the temperature variation as a function of, again, radius. Okay, so this is a type of example for the heat transfer conduction problem, and using boundary condition in order to solve the Cartesian, the cylindrical, and the spherical. I'm not go there. I'm not give you some example of the cylindrical and spherical. Okay, by assuming that you can understand this example from the textbook exercise or textbook example. Okay, so please make sure try to understand the example in the textbook. Okay, so that you can see clearly the difference between the cylindrical, the Cartesian XYZ cylindrical coordinate as well as spherical coordinate. Okay, like I say, cylindrical and spherical is not common. So not common, not famous in terms of analysis. Especially for the spherical, it's not common. Okay, cylindrical is probably useful in order to analyze the tube shape, the cylinder shape. Okay, that is more common. But for spherical is again less common when you want to analyze heat transfer in the spherical type. Okay. Okay. Any question? So basically, our syllabus is only until this one. Okay, there is heat generation, but heat generation I will explain in the later in the chapter 3. Okay, in the chapter 2 there is some heat generation, but I will explain more in the chapter 3 topics. Okay, so basically we finish the chapter 2 until this derivation of the temperature distribution and how to solve the problem of the heat conduction equation. Okay, heat conduction equation. Okay, next one I will give you some assignment related to this exercise or this topic. Okay, on how to use the heat conduction, general heat conduction equation. Okay, and apply the boundary condition in order to solve the problem of finding the temperature and the heat transfer. Okay, so use the example textbook in order to strengthen your understanding. Okay, so if you're not sure, you can ask me personally or you can ask in the group as well. Okay, so with that I think I end my presentation. Okay, any questions so far? I hope you got a clear you can get clear explanation on how to solve the problem related to the heat conduction equation. Okay, because next topic we will go to the a simple heat conduction analysis at which we only use more on the steady state. Okay, this is heat conduction equation. So we finish this one. We finish the heat conduction equation until this solution. This one, okay. And then next one we will go to the steady heat conduction. Okay, at which we will use the techniques called thermal resistant analysis or thermal resistant concept in order to solve heat conduction problem. Okay, guys. So with that, I end my presentation. So,
Hello, Doctor. Hello.
You have a question?
Yes, ada question.
Yeah, Syahrul Razin.
Untuk problem yang 258 tadi,
Okay.
T infinity tu sama dengan T2 ke? T 0.4?
T infinity is not T2 because okay. Okay, I understand what you meaning about the.
Saya tak pasti macam mana nak dapat C1.
Sekejap mana tadi yang saya draw? Saya dah cancel. Okay, this one. Okay. At this part, okay, of course, the temperature at here is T2, but T2 is not given. Okay, T2 is not given. However, the boundary condition given is T infinity 25 is at surrounding. So T2 is not equals to the T surrounding. Okay, probably T2 is close to the T surrounding but not 25 degrees Celsius. So how to solve this? You need to do some, okay, In fact, you, okay, if I can, okay, let's say if we can solve this, okay, okay, from this step you can find the next analysis. Okay, so using this second boundary condition, okay, so at x equals to L, okay, okay, you know that T x equals to C1x plus C2, okay, so if T equals to L, C1, sorry, this is not C1, this is a CL. So C1L plus C2, correct? Okay. You know that C2 is a 90 degrees Celsius. So this one, C1L C1L plus 90 degrees Celsius. Okay. Okay. So using the so this is your TL. Your value of TL okay, the TL here, so the TL equals to C1L plus 90, so it's basically your T2. Okay, kalau you nak label as a T2, if you want to label is T2, okay, T and L. Okay, so using the boundary condition here, okay, so this TL, biru so this TL you will be put into this calculation. You know this. You know that this dtdl over x. Maksudnya you need to find here the terms of if you got this k value, you need to find this term dtl over dx. Okay. So this one is basically C1. So what is the C1? You need to find from here. So you need to rearrange this equation. C1 equals to TL minus 90 divided by L. Okay. So you put all this term in this expression and try to solve this equation so that you can get what is C1 value. Okay. Paham tak? If you're not very clear, sebab saya punya space ni agak limited. Okay, I think I can find some Okay, look to this example here, where you have convective, yeah, this one. Okay, so this example 213, okay, this is a heat flux, this is a convective, this is a heat flux, this is convective. Okay, look how this problem solved by solving the problem of convective boundary condition. Okay, so first they take the second boundary condition, okay, and then they replace the term with the C term, C1 and C2 terms. Okay, so dt dx replaced by C1, and then TL you replace with the term C1L plus C2 that we just do it right now, and then T infinity maintain as it is, H value. So you rearrange this so that you can find the C2 terms. Okay. Here C1 is negative Q naught divided by K, but in our case C1 equals to 90 degree Celsius. So you just replace C1 with a 90, and then you should get the C2 term. Once you can get the C2 term, you know that Tx equals to what just now? C1x plus C2. Okay, so you can find the final terms of temperature variation in the wall thickness, okay, as a function of thickness, as a x value. Okay, boleh. Siapa tadi yang tanya? Syahrul
Faham Doktor, thank you.
Okay, so try to look the example in the, probably the example is not same as the your as required, but some of the boundary condition is a common, so you can follow how the boundary condition expression and solution in order to solve the problem. Okay, so if there is no question, I give you back the QR code. Okay, so please try to do some exercise on this particular topics, and then I will give you the next assignment, okay, in the e-learnings. Okay, so with that, thank you very much for your attention, and see you again in the next class. Okay, assalamualaikum, and good day to all of you. Okay.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Apa dia? Fahmi? Okay, okay. Sama-sama.
Thank you.
Saya tahu dulu. Okay.